Thank you for joining. I'm Akshat Aranya, Senior Software Engineer with AWS Global Accelerator.
And I'm Alan Halachmi, Director of Solutions Architecture for Worldwide Public Sector at AWS. In this session, we'll share how AWS delivers highly available global traffic management at scale for our customers. Before going into the details, we'll motivate why we built a service to deliver this capability. Then we'll cover how we think about availability, and we'll round out the session sharing some cool features like source address preservation. At AWS, we work backwards from our customers. 90% of what we built is driven by what customers tell us matters. The other 10% are things we hear from customers where they may not articulate exactly what they want, but we try to read between the lines and invent on their behalf. Customers told us that they wanted low latency, high availability, consistently performant WAN-optimized network connectivity between users on the internet and their applications in the AWS cloud. DNS-based CDNs were fine, but they relied on clients to honor DNS server responses. Our customers wanted service-side control over the edge experience. In response to this, we built AWS Global Accelerator. Global Accelerator is a service delivered through 104 points of presence at the edge of the AWS network. For each customer instance of a Global Accelerator, the service presents 2 static IPv4 addresses and optionally 2 IPv6 addresses. These edge locations then route traffic to endpoints in 1 or more AWS regions, optionally retaining the source TCP/IP headers based on the customer-defined configuration. The service is built for 4.5 nines when both IP addresses are used and connects internet users to 21 AWS regions. Global Accelerator is optimized for both front-end client and back-end endpoint TCP connection setup. With client TCP termination at the edge, we can pipeline the 3-way handshakes with the client and with the endpoint, reducing the time to first byte for the client. Additionally, we tune TCP parameters for the front-end client and the back-end endpoint to drive performance across the AWS global network, resulting in 60% improvement in throughput. Getting availability right on the internet is not simple. Global Accelerator is designed to account for failure at each leg of a packet's journey. Here you can see several categories of failure we account for. While we won't have time to cover all of these scenarios, Akshat and I wanted to cover a few failure modes we think you'll find most interesting. At the high level, each of our edge points of presence peer with external networks using the AWS border network at our transit centers. Traffic from these autonomous systems traverses our border network before it's processed by the Global Accelerator stack. Global Accelerator uses Anycast addresses, advertising these statically assigned addresses through multiple POPs. This approach allows traffic to flow seamlessly through another POP in the event any given POP is impaired. As a result, no DNS or client-side changes are required. Each Global Accelerator point of presence provides 2 independent network zones per customer accelerator. The network zones are independent hardware and software stacks. Each network zone is responsible for 1 of the 2 IPv4 and optionally 2 IPv6 Anycast addresses per accelerator. Within each network zone, we employ a cellular architecture that allows for independent, isolating failure domains within the networking zone. Finally, we shuffle shard customers across the cells in the network zones. With shuffle sharding, we're able to reduce correlated customer impacts in direct proportion to the number of cells we have. We've discussed shuffle sharding in previous networking at scale presentations, but as a reminder, shuffle sharding takes advantage of combinatorics to improve overall operational performance. With regular sharding, there is a consistent shard to resource mapping. Any given shard is the same resources for any user of that shard. With shuffle sharding, the resources underlying the shard are consistent for a given customer, but generally not between customers. For example, I put customer 1 on cell A in one network zone and cell B in the other. That's customer 1's shard. I place customer 2 on cell A, overlapping with customer 1 in one networking zone. But I put customer 2 on cell D in another networking zone. In this way, we can isolate impacts related to customer 1's shard from other customers like customer 2. By leveraging each of the two IPs in the shuffle shard, clients experience only negligible, if any, impact if one of the cells is constrained or unavailable. Now that we've talked about single POP resiliency, let's hear from Akshat about multi-POP considerations. Akshat?
Thank you, Alan. As Alan mentioned, Global Accelerator advertises its IP space from multiple POP locations. This is achieved by placing BGP speakers inside POPs, all of which are advertising the same IP space to the internet. A client is routed to the closest POP location. Once the traffic lands at a POP location, it is routed over the backbone to the nearest AWS region where a customer's endpoints are located. In rare situations, a POP gets isolated from Amazon's backbone and AWS regions. This leads to an interesting problem where clients that are connected to an isolated POP see an availability loss. As an example, traffic from client B lands at an isolated POP, but is unable to reach any region because its link to the backbone is impaired. In such situations, operators need to use an out-of-band channel for communicating with border switches so that the routes can be withdrawn. This can take sometimes up to 30 minutes, during which availability will be lost. To reduce impact of such incidents and to improve the availability of Global Accelerator, we recently took an alternate approach for how we advertise BGP routes to the internet. We moved the BGP speakers from POPs to EC2 instances running inside AWS regions. These BGP speakers set up their session with the border routers of a POP. As a result, when POP isolation happens, all of the BGP speakers lose their connectivity with the routers that they connect to. Their session gets dropped and external-facing routes are withdrawn. Because of the anycast nature of these routes, traffic that was previously coming in to the isolated POP now migrates to other POPs. As an example, the client B, which we saw in the previous slide, now moves to the first POP instead of continuing to send traffic to the second POP which got isolated. When designing the system, we carefully determined the right level of redundancy required for BGP speakers to meet our availability goals. We arrived at the number 4. Each POP location has 4 BGP speakers placed in 4 different AWS regions. More BGP speakers would add needless complexity with no significant gain. Further, we needed to manage the number of routes we install on our top-of-rack switches and other switches upstream from there so that there is room for future expansion of our IP space. Using redundant speakers also allows us to continuously deploy software upgrades. We can take down one of the 4 speakers, knowing that there are 3 other BGP speakers announcing the same routes and there would be no loss to availability. Also, in case we get a bad deployment, the blast radius is limited to 1 out of the 4 speakers, which minimizes our risk. Now let's look at another aspect of CDNs which we wanted to address. Typically, CDNs use network address translation to route traffic from an edge location towards an origin. Also, the origin generally needs to be publicly routable so that the CDN can route to it. In this example, the packet seen by the origin is sourced from a NAT IP address of an edge location, 7777. The end client's IP is not a part of the IP header and instead is encoded in an X forwarded for header for HTTP proxies. For layer 4 load balancers, the edge host may use proxy protocol to pass on the client's identity to the origin. In either case, the application that's hosted at the origin needs to be aware that there's a proxy in the middle and the client's identity is encoded somewhere else in the received packet. When we initially launched Global Accelerator, this was a mode that was used for routing. However, our customers overwhelmingly asked us to provide client IP preservation. With client IP preservation, an endpoint directly sees the IP address of the client that's communicating to it. This makes it very easy to move existing applications to Global Accelerator without losing the ability to identify the client that's connecting to the origin. This also allows an origin to be completely hidden. Global Accelerator can route traffic to private IP addresses inside a VPC. We achieve this by encapsulating the original packet that is received from the client. The encapsulated packet has an outer envelope that contains enough information to tunnel traffic into the VPC and to route return traffic on the same path. Let's see how this actually works. In this slide, we have a typical setup for Global Accelerator. Client 1234 connects to the global IP 5678. When the traffic is received by Global Accelerator Edge, it selects an endpoint 10234, changes the destination IP address, puts an encapsulation header, and sends the traffic towards the VPC. This traffic is received by Global Accelerator ENI within a customer's VPC. This ENI will then remove the encapsulation and pass on the traffic to the instance that is receiving the traffic. Then the instant response to the packet flips around the source and destination addresses. And then it uses a special property of routing called return to sender, which then sends this packet back to the Global Accelerator ENI and not following the routing rules of the VPC. An encapsulation header is attached to the packet, and the packet goes back to the edge location where it came from. And finally, the edge location removes the encapsulation header, changes the source IP address back to the static IP address of the accelerator, and sends the traffic back to the client. As you can see, both the client and the endpoint are completely network transparent. Let's talk about another problem that service operators often run into, especially with CDNs. CDNs typically use DNS for traffic management. DNS resolvers use geolocal DNS records to direct clients to IPs of a nearby POP. These DNS records are also used to manage traffic and to migrate traffic when application configuration needs to be changed, as an example for blue-green deployments. However, clients and ISPs do not play well all the time. They do not respect TTL and cache DNS records far longer than a service operator could hope for. As an example, we recently migrated our API service to a new load balancer. When we moved its DNS record from the old load balancer to the new one, we saw that a majority of traffic quickly moved off of the old load balancer, but we continue to see some traffic on the old load balancer for about 2 hours. Now let's see how Global Accelerator helps to solve this problem. Alan?
Thanks, Akshat. The key idea to solve the DNS problem is not to rely on DNS at all. Global Accelerator provides static IPs for an accelerator that can be used by clients either directly or through DNS records that never need to change. All traffic management is handled behind those static IPs using service reconfiguration that is much faster to propagate and does not rely on client behavior. Global Accelerator provides 2 knobs that customers can use on their accelerators for managing traffic distribution: traffic dials and endpoint weights. Traffic dials control the percentage of traffic we determine should flow to a specific region, the closest healthy region, that is actually routed to that specific region. In this example, with 60% set for US East 1 and 100% set for US West 1, all of the traffic we determine should flow to US West 1 is routed to that region. However, only 60% of the traffic we determine should flow to US East 1 is actually routed there. The remaining 40% of the traffic, for which US East 1 would have been the desired region, instead flows to US West 1. In another example, if we set both region traffic dials to 50%, half of the traffic determined to flow to each region is instead routed to the other region. This region-level steering is useful when you want to upgrade an application in a region, dialing down to 0%, or drive some portion of traffic to another region for operational reasons. Endpoint weights determine the portion of traffic that Global Accelerator directs to endpoints in a region. Weighted routing lets you choose how much traffic is routed to a resource in an endpoint group. This feature can be useful in several ways, including load balancing and testing new versions of an application. Even so, Global Accelerator is designed to fail open and will disregard traffic dials and waits to deliver traffic to an endpoint if all endpoints appear unhealthy. Routing both for traffic dials and endpoint waits happens independently within each packet processing pipeline at the edge receiver. We hope that the session provided a useful glimpse into how AWS provides highly available global traffic management at scale. If you have questions, we're happy to answer them during the live session.
Thank you so much for your time.
Bye.